Okay, hello everyone, welcome back to the channel. My name is Mutanda Samil, and now this time around we are still proceeding with our series of Aitel revision. In fact, the marking guide for Aitel physics. Alright, now we are in for item 4, and as you're watching item 4, please, you must have also watched anyway, we have right here from item 1, item 2, item 3, and item 4 of our Aitel Moko examinations. Okay, so we are trying to get the guide or the possible solutions to the possible responses in simple terms to some of the items which were set by Aitel Moko examinations board. Alright, so without wasting time, I think let's get to the point right there. Alright, good. So we kindly call you to subscribe to the channel. Please subscribe, and also subscribe. Please don't forget to share, like, and also you have to comment on the channel. Okay, so you realize that, please, we are in for item 4, and please, we beg you to list. Okay, check in the playlist, and please you watch the videos right from item 1. But as you are looking into the mock revision items, like we are in for Aitel here, please, in the playlist we have physics. Do we have physics revision items? You check in the playlist, there are over 16 items there, good enough for you to at least go through them. And you never know, our prayer is only simple that maybe what you have gone through has something in common to do with it, the forthcoming exams. Of course, who knows, you find that a question at least part of it may be brought, and with that, of course, you'll be able to score some good grades. If you're a teacher, then your students will be able to score some good grades. Okay, we again call for your support by subscribing to the channel. Okay, now without wasting time, I think let's get to the point. The question, we have it revised. Okay, good. So you're in for Aitel mock examinations. Specifically here, we're going to deal with physics in simple terms. Let's read slowly and we try to reason out. Please, this item is about heat. However, it was combined simple, in fact, machines, simple machines, and heat. Okay, what we call calorimetry, where we have the specific heat capacity and so on. That's what we're going to have in this item. So please, you watch the end. Of course, this is item 4. Okay. Now, without wasting time, I think let's get there. Now, here I'm not minding about the sections. You all know how the sections go. Section A has how many questions? Section B part 1 has how many questions? Section B part 2 has how many questions? Please, if you don't know that, you check in the playlist. We have a video explaining all that. Okay. So without wasting time, I think let's get to the point. We go through it. So they're saying, an engineer and his employee had a disagreement. Oh, anyway, that's very bad. An engineer and an employee, that's not in Africa, really. Of course, you lose the job there and then. Okay, anyway, an engineer and his employee had a disagreement on the best type of simple machine to use when raising the tank of weight 600 newtons on top of a raised platform on a building of height 12 meter. Okay, good. The machine is available with a block and tackle pulley system of velocity ratio 5 and 36 meter long, requiring an effort of 250 newtons, and an inclined plane 244 meters long, requiring an effort of 400 newtons. Okay, good. The tank was to be used to supply cold water at 20 degrees Celsius to the rooms of clients, to mix it with hot water of 80 degrees Celsius to attain a bathing temperature of water at 35 degrees Celsius. Okay, good. Hint: each heater in every room boils 2.5 liters of water. Right, there we are. Then also, specific capacity of water is 4,200 joules per kilogram per Kelvin. The density of water is 1,000 kilogram per meters cubed. Right there. So let's go and see what do they want in the items, or rather the tasks. So they're saying task: as a learner of physics, part A, analyze. Anyway, It was meant to be analyzed here. Anyway, analyze the information and use it to settle disagreement. I think that's about carrying the certain load. Okay, help the engineer determine the amount of cold water that will be supplied to the clients. Okay, anyway, these engineers have some task here, but again, what they're going to do, our area of consultation is going to be here. Look, they want us to help them settle the disagreement. Now we must go back in the question and check where is that disagreement. So that part will help us get this part all right answered. So with this, now they're saying an engineer and his employee have disagreement on the best type of simple machine to use in raising a tank of weight 6,000 newtons, 600 newtons to the top of a raised platform on a building of height. So the building is of height 12 meters and the body you're carrying, the load is of weight 600 newtons in simple all right terms. Okay, how do we have here? Okay, machines, the available machines were block and tackle pulley system of velocity ratio 5. So let's begin with that. So we're going to allow me just have this here like this. We have what we call a pulley. Allow me just call it a pulley system of velocity ratio 5. So velocity ratio of this pulley system is simply 5 VR is equal to 5 is summarized. Do not tell us. Okay, velocity ratio 5 and 36 meter long. 36 meter long. Anyway, the pulley system is of 36 meters long. It means that its length, because I don't want to use load, because yeah, they're like the length of that length. Allow me write it like this, because I don't want to write L, because L may mean load in the machine. So the 36 meters, this may not have really any impact here. So okay, requiring an effort of 250 newtons. So an effort E will be of 250 newtons. 250 newtons. Okay. All right, good. So let's see. Continue. All right, good. So they'll have to 15 newtons, but remember the load, a weight, the weight they're going to carry is of weight 600 newtons. Therefore, it means that that weight you're seeing there, that weight is same as a what? A load, and the load is how much? 600 newtons. 600 newtons as such. So now what we're going to have here next, you realize that we have a pulley system, a block and tackle pulley system, but also we have what we call an inclined plane. So an inclined plane, let's get it drawn here. Now an inclined plane here, realize that here we have an inclined plane like that. So an inclined plane here we're going to have, it is of length, rather the load, remember they are carrying the same load, a load of 600 newtons. Because the engineer and the employee, they are arguing that the load of 600 newtons can be carried using a pulley system and an inclined plane. Now they want you to help them to settle the disagreement. Which one is better? Anyway, you can't just tell by your eyes and say this one is better without a reason. Of course, scientifically, we must go via calculation such that we get that done. So inclined plane of 224 meter long. Now the inclined plane here of 244 meters long. Allow me to draw it here. That's our inclined plane in that format. So that length they are telling us of 244 is the length right here. 244 meters long. This length here is then their meaning like that. Okay, then next, okay, requiring an effort of okay, 400 newtons. So if you have the length there, you have to know that the effort E, is equal to 400 newtons. Now next, what do we have about this? All right, good. So like that. Now remember, they want to carry a body up to how much? They want to raise the platform on a building of height 12 meters. If they want to carry it up to there, then it means that even the inclined plane must be of that height. The height of the point where they want to put the load must be equal to the height of the height of the inclined plane. Inclined plane is more like that, like we have drawn. So here it is 12, also 12 meters. Now the question comes, what are we going to calculate in order to be able to compare these machines? Now when you talk about machines, please, and if you want to compare about their mode of work, please, you must always consider what you call the what? The efficiency, if you can really see that. So but how do we get efficiency? You all know that our efficiency is equal. So we're going to calculate efficiency for the pulley and also efficiency for the block and tackle in terms of, in fact, a frequency for the pulley system and a frequency for the efficiency for the inclined plane. We compare. Of course, if the percentage is big, then that will be the best machine to use. And I think with that, let's go to the question and get there. Right, good. So let's go and get there to the question. Part A, we get it answered. So we say, part A, we are starting with our pulley system. Now a simple reminder, weight of the tank. Okay, simple reminder, you have that. Weight of the tank, comma L equals to 600 newtons. Then also, of course, our summary will be load is equal to 600 newtons. The effort was 250 newtons. Summarize the other side earlier on. Velocity ratio, comma VR is equal to 5. And then also we know that efficiency of a pulley system. Now, efficiency, comma, let's have its formula. The symbol for efficient is that. And now, please, let's get to now we pronounce this. This symbol here is pronounced as this. This symbol here is pronounced like this. Eta. This is eta. We call it eta. That's the symbol that we have, eta. Please have very many symbols. This symbol here is called alpha. You can really check into that. That symbol is called alpha. The symbol of this format. This one here is called the mu. Symbol mu. Actually, we have very many of them. We have this one in that format. We call it omega. So in science, you don't need to just go and have one day just to learn about them, but any topic you cover brings about some of those symbols and their names. So the symbol for frequency, for efficiency of machines, we call it eta. Okay, good. Now with that, we have that if efficiency is equal to mechanical advantage over velocity ratio times 100. That is the formula for efficiency we're going to use here. Okay, the best one, of course. Why are we using this? Is because it has velocity ratio, and part of this we have velocity ratio given to us. That's why I've chosen to use this formula specifically for frequency. But again, a question of doubt comes in. Do you have the mechanical advantage for the pulley system? We don't really have. Please, all what you have summarized here works for only the pulley system, but do we have, in simple terms, do we have the mechanical advantage? We don't have it. Then it means that we must go ahead to calculate mechanical advantage. So it says that mechanical advantage is equal to load over effort. But do we have load? Yes, here it is. Do you have effort? Yes, here it is. Then we shall be able to get the mechanical advantage. So by substitution, you see that we have a 600 divided by 250, and when you divide, you get mechanical advantage as 2.4. Please, here we don't put units. Here we don't put no. We are just say no units. We don't put units on mechanical advantage because it is a ratio in simple terms. Okay, good. Now, since you have the mechanical advantage as that, we have the velocity ratio as this. Then you can multiply and have the frequency or the efficiency. Sorry, I'm instead calling it frequency, but I don't know why. But okay, it is the efficiency. Okay, and efficiency simply means how better a machine can do work in the shortest time possible. Like I will compare you, if you want to know what you call efficiency, if you have maybe, for example, if you have this, for example, have a bicycle. If you want to know what to call efficiency, that you have a bicycle, and just from where you're watching this video from to up to the trading center. Okay, just imagine if someone is using a bicycle, that's one way, and if someone is using a motorcycle, that's one way. Which one is a bit cheap to use? It is a motorcycle. It is faster and use less energy. A bicycle also moves fine, but uses more energy. So a motorcycle has a bigger efficiency compared to a bicycle. I don't know if you can understand that. Anyway, that is what we can simply mean by efficiency. And now efficiency tells us how better a machine is. And with that, let's go and make the substitutions. So we shall remind ourselves of the formula for frequency, that eta is equal to mechanical advantage over velocity ratio times 100. And then we shall have that substituted. We have the efficiency as the mechanical advantage as that, and the velocity ratio as 5. We try to compute this in your calculator. The answer must be the percentages. So eta will give us 48%. Okay, good. So that's what we have so far. Now what does it mean? It means that the efficiency for this one is 48%. Now you must go ahead, you have calculated for Pulley system, you must go ahead and calculate the one for inclined plane also. Then we compare the two answers and we see which one is super good or which one is better. Let's get there. So we say inclined plane. Now there, to remind ourselves, the load is originally 600 newtons, not changing. And please, the load is the same because they want to use the same load and they see which one works better. So we are having the same load right there. And efficiency is, rather effort is 400 newtons. Now, a pulley uninclined plane appears like this, uninclined plane. And an example of uninclined plane, please. An example of uninclined plane, yeah, can be a ladder even. A ladder, well, but that cannot bring it out very well. Just imagine maybe if they place a piece of wood. Anyway, a ladder also can work as an inclined plane. A ladder, okay. If you were to walk on these steps there of the ladder, then we made that sort of made by an inclined plane in simple terms. Or for those who have ever gone near, okay, where they offload and load stuffs on vehicles, if you ever seen that, they can put something here, then they bring something here, they roll it, they move it up to when it can enter the vehicle. In simple terms, that's what we mean there. Or in simple terms, if you have a load over here and they are carrying it up, sometimes they even put a simple pulley here, a rope, then they will start pulling this load. As this one goes up, this rope comes over this side. That's what we simply mean by, okay, an inclined plane. It simply appears like that. Now let's put the lengths in here. So we have 12 meters there. Why 12 meters? Because the body they are carrying, they are carrying an object on a height of building, on a building of height 12 meters. So it means that the height of the building must be the same as the height of the, okay, height of the inclined plane, such that the object can easily reach the height of the building in simple terms right there. So with this, let's get the numbers labeled. Now what you must know is that load mechanical advantage is equal to load, of course, just like the mechanical advantage here. Now we're going to use the same formula. This very formula I've used here is one we're going to use even right there. So let's calculate the mechanical advantage. Mechanical advantage is equal to, we have the load here 600 and effort as 400. So the mechanical advantage will be 1.5 in simple terms. If you have the mechanical advantage, what is missing? We now don't have velocity ratio in simple terms. And then how shall we get the velocity ratio? Of course, you must learn from this. So velocity ratio is equal to distance moved by effort over distance moved by load. This is how we get velocity ratio as far as okay, inclined planes are concerned. Hope that really makes some sense. You need to memorize this formula here. Velocity ratio as far as inclined planes are concerned is the distance moved by the effort over distance moved by the load. But then how do we tell the distance moved by the effort? How do we tell the distance moved by the effort? Please, what you should know is that if you are carrying, we are carrying something from here up, what you are carrying must always be here. So this one here is our load. Our load, in fact, this one here is our load, and we are to carry this load, we pull it upwards. So when you are pulling, we pull in this area here. Or in order to know the distance moved by the effort, is that biggest value always in the hypotenuse. So here the okay, effort, distance moved by effort, always take the hypotenuse, and distance moved by the load, you always take the height of that given, okay, of that given inclined plane. So please, if they want distance moved by the load, you take this height. If they want distance moved by the effort, you take this. That's what we mean right here. Okay, good. So this is distance moved by the effort and distance moved by the load. I've clarified. This one is for the hypotenuse, and this one here is for the okay height in simple terms. That's how you get that done. Then let's substitute there. So velocity ratio is equal to 44 over 12, and our final answer will be 20.33. Still, velocity ratio doesn't have a unit. We don't have an SI unit as far as velocity ratio is concerned. With this, let's move again. We can see how we can substitute this in the formula of efficiency. So shall we say efficiency of an inclined plane, comma, eta equals to mechanical advantage. Eta equals to mechanical advantage over velocity ratio times 100. So now eta will be given us, remember our mechanical advantage is 1.5, and our velocity ratio is 20.33. Multiplying by 100. Remember the other first one was 48, so we pray maybe this one will be what? Okay. When you substitute that, you get 7.3770%, or simply it will be 7.4%. If it's a percentage, you can report one decimal place acceptable. So are you seeing we have this 7.4%, then this side we had what? For the block and tackle system we had 48. Meanwhile for this side, look at this, for this side we have 7.4. so which one is better? I told you the bigger the percentage, the better the machine. That brings us to the conclusion that indeed the block and tackle system is the simple to use. So it is better to use a pulley than inclined plane because the pulley system has a higher frequency of 48% compared to that of an inclined plane. That gets our part A of this question answered. Okay, hope you have really learned something here. And of course, the next part is one which is very, very interesting. Guess what? It's all about heat. Okay, let's go there. So part B, they're saying, let's make some analysis here. Part B, they're saying, help the engineer to determine the amount of cold water that will be supplied to the clients. But again, that's talking about cold water and so on. Let's go and make some analysis, a breakdown in simple terms. Analysis or a breakdown in simple terms. Okay, let's get there now. So realize that here. Alright, so now we realize that here we have, now the whole story starts from here. The tank was to be, okay, we have this. The tank was to be used to supply cold water. Are you seeing that? So it means that here we have cold. It means that we have cold water in there. Okay, cold water at how much? Cold water is at 20 degrees Celsius. Okay, what next? To the rooms. So this cold water is being supplied to the rooms. Now maybe this one is the room here, right here. To the rooms of clients to mix it with hot water. The rooms of the clients to mix it with the hot water. Now we're going to mix it with hot water of how much? This is our hot. Okay, so now we're saying that this is our hot water in simple terms, and this hot water is at 80. This hot water is at 80 degrees Celsius. Now what must you know is that now they're saying, remember that they are saying to mix this hot water with this, to mix. Now what must you expect here if they are to mix? In fact, to attain a bathing temperature of 35. So therefore it means that after mixing, you shall have a final temperature of the water. Like we have this final temperature of the water as 35, like that. Now what does it mean? It means that, okay, when you mix 20 degrees with 80 degrees, the final temperature will be 35, of course enough for bathing. Now let's go and see that in that sketch will help us get the calculation done. Let's go there. Okay, so we're going to part B. We're going to get part B answered. Okay, now part B begins with that. Please allow me to use those spots there to at least illustrate some of the things we have there in the question. So realize that this is our cold water, and this is our hot water, and this is after mixing. Of course, you know what it means by mixing. Now, of course, this one is at 20 degrees Celsius, this one is at 80 degrees Celsius, and this one is at 35 degrees. This is theta 1, this is theta 2, theta 3, and theta 2. Now, why are we giving that? Is because we are giving those thetas in terms of which temperature is highest. The highest temperature, the lowest temperature is theta 1, followed by 35, and the highest is 80. That's why this one is number theta 1, this one is theta 2, and this one is theta 3. In terms of which one is the highest, if you can really see that. Now, what you're doing, since I've said they're mixing, so you see our pipe is trying to pour the water from this side up to there. It's pouring the cold water into hot water. Now, what do you expect here? Now in physics we have what we call heat gained must always be equal to heat lost. You all know about that if you learned the calorimetry, or if you didn't learn, you take it from here. So heat gained is equal to heat lost. An implication that the cold water would gain heat, the cold water will gain heat. You see that? Then the hot water will lose. Okay, the hot water will lose heat in simple terms. So that's what it means that heat gained must be equal to heat lost. Now what does it mean? We must look at the quantity of heat produced here. The quantity of heat, what must we know? The quantity of heat Q, the heat used to boil any water. We take a mass of that water times the specific capacity of that water. Remember the symbol for C is the symbol for specific heat capacity, like that. Then times the temperature changes. The temperature changes, so I can call it delta theta, the temperature change, which some people program as theta 2 minus, okay, theta 2 minus theta 1. That is it. But again, what must you expect is that, let's go and see that in the next part. Now still we shall say that from there, and when you mix that, you realize that it will give us this mixture here. But again, we start from here. Cold water loses heat, gains heat. Hot water loses heat. Let's get that acronym here. So we say that heat lost by the hot water at 80 degrees Celsius is equal to heat. Okay, by the way, this is not meant to be lost, but it's meant to be gained. Sorry, this is meant to be gained by cold water at 20 degrees Celsius. Now if it is gained, then what must you know? If this one is at 80 degrees, what you are saying, since you have a temperature at this level and they have a temperature at this level, now they must all get what we call a pattern. A pattern here will be this other counterpart, which is 35. You see that? Then here also, this 80 degrees also must have a pattern from here. Must have a pattern from here. This 80 degrees must have a remaining pattern, which is 35 also. So 35. Since we mixed the 80 and it gave us 35, so it means that this 20 and 80 contributed to the coming of 35. So that's why I have 80 and 35 again. This 20 also contributed that 35. That's why I have a 20 and 35 degrees. Now what must you know? Now the temperature changes will be how? Look at this. The biggest minus the smallest. The biggest is 80. If you can really see here, the biggest is 80 minus smallest, which is 35. You can really see that. What about this side, whereby the heat is being gained? Heat gained, sorry, it's meant to be gained, not necessarily lost. So heat gained will be what? Highest is 35 minus lowest, which is 20. If you can really see that. We don't accept negatives here, so we shall say, but since this one is hot water, we shall say, remember I said the quantity of heat is equal to mass times specific capacity times temperature changes, which can be theta 2 minus theta 1, depending on the question you're dealing with. So the mass is done we have right here, specific capacity is done we have right here, temperature changes done we have here. Now why are we doing like that? One would ask, why are we saying theta 3 minus theta 1? I said you compare, we have this one at 80, but you compare it with the final temperature with 35. The biggest is what is 80. So that will be theta 3 minus theta 2. We have it right here. Theta 3 as that, theta 2 as that. Then here also, this 20 also brought about that 20, that 35%. So we shall have that is equal to mass into, now temperature changes, it will be theta 2, the 35 minus theta 1, which is a 20%. That's the 20 degrees. Okay, centigrade or simply Celsius. Now, what we must know here is that mH is the mass of the hot water. Specific capacity is the mass of water. Now, whether water is hot or what, the specific capacity of water, pure water, is known and has been given in the question. Now, this one is the mass of the cold water. Specific capacity of the cold water, which is always the same, whether water is hot or not. Specific capacity remains the same. Theta 2 is right there, and theta 1 is right here. Here, theta 3 is right here, and theta 2 is right there. Hope you're on the same page. Next is substitution. Remember, our question wants us to find out the mass of the cold water they added, like the mass of this water, how much did they add in order to come to the temperature which we have at 35. So with that, we substitute. You find that we have. So But mH, do you have mH, the mass of the hot water? Do we really have it? Not really. But remember, in the question they said this. Remember in the question they said this. Please, in the question I had this, that each heater in every room boils 2.5 liters of water, meaning that the water which is at 80% was 2.5 liters. But again, since you have liters, remember liters is a unit of a liter. A liter is a unit of volume. So you need to find the volume, and of course I want mass. We want mass. But you know that from this formula here, acronym, from this acronym here, you realize that mass is equal to density times volume. If you can really see that, mass is equal to density times volume. We get that converted first of all. Let's go there. So we know it is 2.5 liters of water, since that's what the heater is heating, and that is water boiling at 80%. So what mass of hot water? So shall I say that, reminding you that each heater in every room boils 2.5 liters of water. Now that's a simple reminder that if they are boiling 2.5 liters of water, it means that the water at 80% was of volume 2.5 liters. But of course, remember, we are not allowed to do any calculation when you have not converted the units to the standard units. We have liters, but the volume is measured in, okay, we know it is meters cubed, but for now let's take it liters to centimeters cubed. Then we shall get from centimeters cubed to meters cubed, which is the standard unit for volume. I think with that, let's get there. I think so we shall say that a simple reminder, but 1 liter equals to 1000 cubic centimeters. Okay, I don't know whether that is real, eh? Okay, understood. So to convert it to liters, you simply multiply. To convert liters to centimeters cubed, you simply multiply. So we get the number of liters times how much 1 liter has in 1000 centimeters cubed. So V is equal to 2.5, which is this, times 1000, which I have right here. When we multiply, you have V volume is equal to 2500 cubic centimeters. But again, we said volume is measured in meters cubed, so you must get it converted in meters cubed. How shall we do that? Let's go to the next step. Now here we're going to use a table still for simplicity. We're going to use the table here. For simplicity, let's use the table. We get the meters converted right here, and also store it away. We are converting the meters, centimeters cubed. We are converting the centimeters cubed to meters cubed. What must you know? First we begin with, okay, in this we can put meters cubed right here and centimeters cubed right there. So meters cubed right there and centimeters cubed right there. Now it all begins from, you all know that we have this acronym that King Herod's daughter Mary drank cold milk. If you can really see that. Now what are we looking for? This one here is centimeter, this one here is millimeter, this one here is decameter, this one here is meter, decimeter, we have hectometer, we have a kilometer. Okay, if you can really see this now, what are you looking at? Meter, where are you? Meter, put a stone in meter. Then you're looking at centimeter, where are you? Centimeter is right there. So how many meters are in centimeters? So you put a 1 in that variable you want to get, then in all the places you put 0 zeros together. It means that 1 meter is equivalent to 100 centimeters. Now what does it mean? It means that if you have 1 meter is equal to that, so it means that a meter cubed will be equal to 100. Also you cube it. What you do this side, you do it the other side. Cube it, centimeters cubed. So 1 meter cubed is the same as 100. Of course, from the original 1 meter is equal to 100 centimeters. We have that as cubed, centimeters cubed now. So we shall have there a 1, and this side we shall have a 100 cubed. Now I've gotten everything into the unit as per the centimeters, the meters cubed. Now, of course, what do we want to convert? We want to convert this. Don't forget, please. We want to convert this. We want to convert this right here. Please, we want to convert this. Let me resolve. We want to convert this into meters cubed. That's our aim. Why? It's because volume is measured in meters cubed. Okay, let's continue. Now here, realize that we're going to have simpler wrap of that. Now here we're going to have the 2500 centimeters cubed. Of course, in the column of centimeters cubed, that's why I put. Then it said I'll have just any unknown which I want to convert, because I want to see this one in terms of meters cubed. That's the way we can convert. So you have that as 2500. You are really keen about that. Then we have this one as our x. Simply we have it in fraction format. So 1 over x is equal to 1000. In fact, when you cube this on a calculator, you get this. You get 1 million. 100 power 3, you get 1 million. Or it's more like 100 times again 100. Sorry. Times again 100. Times again 100. And this will automatically give you the 1 million you have right there. So you cross multiply this times that. This times that. So x times 1 million shall have a 1 million x is equal to 12,500. We want to find the value of x, so divide both sides by 1 million. Dividing both sides by 1 million. Alright, what shall we have the value as the value of x in meters cubed will be 0.0025 meters cubed. We have gotten that converted. Please, our aim is to get the liters into the meters cubed as a standard unit for volume. That's what we are aiming for. And now with that, it means that we can now get the mass of alright, hot water. So mass of hot water is, we don't know, so but the volume is 0.0025 meters cubed, and the density of water, you all know it, it has been given to us here in the question. Please, they have given us the volume of water right here. They have given us the volume of water right here. If you are really keen, they have given us the volume of water right here. Volume of water, or the density of water is this 1000 kilograms per meters cubed. Okay, now, so what you're going to have in simple terms is, alright, now we're going to go back to our part where we were originally. Okay, think right here. Now we have the density as that. Now I think we can get the mass. So we shall say that from, we want the mass here. Mass is equal to density times volume. Now one would ask, why are we in simple terms calculating the mass? It's because in the formula here, I want to be clear on this. In the formula here, please, we have mass of hot water, we have masses, but yet what they have given us is volume. So we must convert the volume into masses from this formula here of mass is equal to density times volume. We have it right here. So from this formula here, that mass is equal to density times volume. Remember, our density is okay. Now mass of hot water will be equal to 1000 times 0.025, like that. So you now get mH as 2.5 kg. Now, a simplest technique, whenever you have volume, whenever you're doing physics and you have volume in, say for example, this one is 2.5 liters. Let me just give you a simplest technique other than using that longer method, longer one, which is will waste a lot of time. So if you have volume in meters and you want to convert this into mass straight away, what you do, you just say mass is equal to, you get that 2.5, okay, divided by 1000, which is density of water, times 1000. Divide by 1000 times 1000. That's how we do. You must show that so that the examiner must see. You find that when you cancel out these ones here, you still come back to the mass of hot water as 2. Okay, you will still come up with the mass of hot water as 2.5 kilograms, just like we have it right there. Because here this method is a bit lengthy, the one I've taken you through, but this one is simpler. Whenever you have liters and you want to convert them into masses in heat questions, you must just multiply by that mass divided by 1000 multiplied by 1000 to show the conversion to the examiner. That is also very, very acceptable. All right, good. Now with that, we have mass of the hot water. Now please, what you didn't know is that we now can bring back our formula. We cannot bring back our formula. That our formula said that mass of hot water times specific capacity of water, theta 3 minus theta 2, must be the same as mass of cold water, which we want to find. We have the specific heat capacity, we have theta 2, and we have theta 1, like that. So we substitute. We're going to have, okay, sorry, I think there's a network error here, but let's get it covered. Okay, now we have the mass was 2.5, specific capacity is 4200, the theta 3 was 80, theta 2 is 35. Now mass we don't know, the specific capacity for water, remember both tanks have water, so it is the same as 4200. Now even if water is hot or cold, specific capacity of water is always 4200, never to change. Theta 2 is 35, theta 1 is 20. You subtract and do the calculations right there. Let's see how the calculations are done. Now with this, you find that When you apply the whole story, multiply this stuff, all this, the answer you get is this, the 472,500, which will be equal to, when you multiply all this, okay, look, when you apply all this, the answer you get is this. But of course, times MC will give you a 63,000 MC. We want the value of MC, so we shall divide both sides by 63,000 on both sides. This of course will cancel out, and then the zeros will cancel the part of the zeros, like that. Next is dividing. What will be the mass here? So the mass MC will be equal to 7.5 kilograms. Saying that the mass of the water which you will add, the mass of cold water to be added. Please, MC means cold water, and MH means mass of hot water. So the mass of cold water to be added will be 7.5 kilogram mass. So we conclude, simply we conclude. So there we shall say that, okay, 7.5 kg mass of cold water was supplied, and that really marks the end of our item 4 of Waukesha physics revision item. I can really appreciate you for keeping on to this up to the end of this video. See you again. Wish you well.